Good evening. So, welcome to the seventh weekly live session for the course Geomorphic Processes, Landforms and Landscape, which is taken by Professor Javedan Malik from Department of Earth Sciences, IIT Kanpur. So, till now we have done fluvial geomorphology. We had also seen the tectonic geomorphology that we did in the last week, and 2 weeks before that we went through in much more detail about the fluvial geomorphic processes, though that is carried out by river. Then tectonic geomorphology dealt with the combination of geomorphic processes that are carried out by tectonic processes as well as some other natural agent also working. So sorry. Okay, so till now we did the two different types of geomorphic processes. Today we will start with another important geomorphic process, that is the geomorphology created by glacial action. So, as we know that glaciers play a very important role in the overall, climate and weather interactions that happens between the Earth, the terrestrial, as well as the atmospheric and your hydrogeological spheres. When we are talking about Earth as a system. So, glaciers usually are found in either polar regions or very high elevated areas, mostly your mountain ranges. So, the geomorphology or the geomorphic uh, so the geomorphic processes that are sorry, the geomorphic landscapes that are created due to the action of glaciers and in areas which are covered by glaciers, as well as some depositional landforms are also created in areas that are situated away from the away from the uh, glacial origin parts. So, as I just explained, that glacial geomorphology is the study of processes, landscapes, and landforms that are produced by ice sheets. As we know, mostly glaciers are formed in the form of ice sheets, as well as they are the glaciers itself are formed due to the accumulation of precipitation, mostly snow, ice, as well as some liquid form of precipitation that then freeze to form the ice, and these together form your glacier. And the movement of these glaciers from their point of origin to the other areas, as and when they melt and they move downhill. So, because of these movements and the freezing and melting action that happens at the base of the glaciers. So, some of more these processes are what cause the changes in the landscapes, and they then form either your erosional landforms or your depositional landforms. And any kind of changes that we see in the landscapes and the landform changes produced by ice sheets, valley glaciers, and other ice masses on the surface of the earth. So, currently 10% of the earth's surface is already, it's under ice cover. And as we know that this percentage area is at risk due to the high temperatures that we are experiencing right now due to the climate change, global warming. So, otherwise, Earth in itself has undergone quite a few uh, glacial cycles in its geological past. So, where a large area of the land as well as the ocean, okay, so a lot of continents and a majority part of the a major part of the oceans also have been covered in ice in geological past, and these were called glacial periods. And between two glacial periods you have the time that is called interglacial periods. So every 100,000 to 150,000 years in the past around in the past 1 million years or so, we've had glacial periods. Okay, so as we are saying that glacial periods, occurrences of glacial periods is common in the Earth's history, but the frequency of it as well as the rate at which the heating of the planet and the eventual cooling of the planet, this rate varies. And currently, due to human interferences, this rate of heating of the Earth is actually it's increasing, and that is why then what we see is that if as we had learned in the starting few classes, how the greenhouse gas effect is actually facilitating this heating of the earth's surface and trapping of the heat, and then eventually when the atmosphere is very densely covered by your clouds and the greenhouse gases, it will not allow the sun's the solar radiation, the solar heat to reach the surface of the earth. So if that happens, then your planet starts cooling, and then what would happen is, since the temperatures drop, most of the areas where you find your where your liquid precipitation gets accumulated, if those areas are not getting the sufficient heat, they will start decreasing in temperature, and if they reach below freezing point temperatures, then the land, which would be the ice cover, starts slowly increasing, and then we would move into a glacial period. So it's a cycle, and we have seen such cycles previously in the earth's past, but the rate of the heating and then the eventual cooling, it might vary right now because of increase in human interferences. So as you can see that in these two diagrams that we see over here, okay, so this is this is the present one. So this is the present one, though this was given in 2000. So and this was the shaded areas, as you can see in the B diagram. This was 18,000 years ago. Okay, this was the kind of the ice cover that was present at around 18,000 years ago. You can see that at present you have ice cover only mostly in the polar areas, like massive ice sheets. The other continental areas for the other continental areas for ice covers, obviously you have some glaciers, in the Himalayan region, as well as other high mountainous regions. You have ice cover in the northern part of the the northern continents, and most of the ice, the maximum amount of ice cover is seen in Antarctica, as we know this. But as you can see, around 18,000 years ago, the ice cover, it slowly started expanding towards the equator. So this is a recurrent thing, but how often it is occurring and what is the period between two glacial periods, that is that can keep changing as in when different evolution changes keep happening on the Earth's surface. So as you can see, the Earth has alternated between interglacial and glacial conditions on an approximate 100,000 to 150,000 years cycle, and this is mostly in the kind of some 20,000 years ago only. So how are these glacial periods calculated, or when how do we know that certain years back we had a glacial period? So what scientists have used are a study using the oxygen isotopes. So oxygen has two isotopes. So one is your 16 and the other one is 18. The O16 is actually lighter in nature and O18 is heavier in nature. So, using the the ratio between these two isotopes, scientists have tried to see whether the current period or the current scenario, whether it is in the warmer period or in the colder period. So that is, warm is the your interglacial time and cold is your glacial periods. So how what exactly is the basis of this is that uh, the lighter the water, okay, so water contains both the lighter oxygen isotope as well as the heavier oxygen isotope. So the lighter the water which has the lighter oxygen evaporates more readily than the heavier water, if you can say. Okay, so how is this information trapped in, say, obviously as we know water is recycled and replenished after a certain period of time in each and every reservoir that is present on the earth. So what they see is these water molecules are sometimes trapped in the sediments itself, and these sediments get consolidated over time, and they can turn into say either layered rocks, or they can be found buried under recent sediments. So there is a technique called coring, that is, we try to derive sediment cores. So when we derive these sediment cores, like these are cylindrical blocks that are drilled out from whichever depth we want to see. So these cores they have a record of this oxygen isotope that is trapped in the sediments due to the trapping of the water that we see. So if it is if it is a warmer if the climate is warmer in nature, so the light oxygen will be more will be evaporated. Okay, so and then the ocean. Okay, so if the O16 is rapidly evaporated, it will be relatively rich in the O18 oxygen. Uh, so when there is warmer, your O16 is obviously evaporated very readily, but your O18 also will be evaporated, since the weather is warm. Okay, so there is much more evaporation, and both lighter and the heavier oxygen, both of them would get evaporated, and the ratio between them is not it's kind of you can say that the ratio remains similar. Okay, but when the glaciers are growing, okay, so because of the precipitation, what will happen is your the O18 will always will be richer in the will be more in the oceans. Okay, because with precipitation again the same kind of concept goes that the O18 will be precipitated out before your O16. So your O16 is still retained mostly in the atmosphere, and your O18 is richer, and then that is why, so we are saying that the oceans will have O18, and when glaciers grow and the precipitation will have the O16. Okay, so these kind of you can see over here that this ratio of O18 to the O16 is calculated, and over the years you can see that how the spikes in the O18 quantity is actually giving you the differences in the the changes in the glacial periods. You have glacial periods and interglacial periods. Okay, so this is how the isotope study of of oxygen can be used. So currently what we are seeing that we are in the interglacial period, and later on with time we might enter into a glacial period. So how long will it take for us to enter in the glacial period? That depends on the rate of heating that is kind of dependent on the human interactions that happens with the our natural surroundings. So then we'll quickly go through how the glaciers are formed. So a glacier is a large perennial accumulation of crystalline ice, snow, rock, sediment, and often liquid water that originates on the land and moves downslope under the influence of its own weight and gravity. So as this is kind of a layered information of the uh, layered information of how the different what are the different compositions and percentage of the structure of the precipitation that is making up the glaciers. So this is your bedrock. Okay, so this is your bedrock, and with actually the depth, if you see, so the depth increases downwards. So the bottommost layer is actually very highly compressed and consolidated glacial ice. Then you have fern, and then you have granular ice, and on right on top you have the more aerated kind of precipitation. So that is the snow, which has mostly air is trapped between the snow molecules that we see. And then with depth you can see that more and more air is kind of uh, the pores, or you can see the voids between the molecules is less and less prone to holding the air. So at the bottom you have the compact frozen ice that we have. So typically glaciers exist and may even form in areas where your mean annual temperature obviously is close to freezing point or below freezing point, and when winter precipitation produces significant accumulation of snow, uh, mostly also in places where throughout the throughout the year you have temperatures that only that keeps the temperature below the freezing point, and it does not it will the temperature never goes above the point where you will have the complete loss of the precipitated snow or ice that has formed over there. So there are a few different types of movements that are associated with the glacial movement. So the first one is your basal slip erosion. So basal slip erosion usually happens with warm based glacier. What are warm based glaciers? Warm based glaciers is the the contact between the bedrock and the glacier that is moving. So there is a little bit of melted you can say melted water between the the glacial sheet that is moving and the bedrock that is present. So, as you can see, the contact between the worm based glacier and the underlying bedrock is lubricated by liquid water, and what the basal slip does is it picks off the broken rock fragments that are present, and it drags along the rock the bedrock that on which the glacial ice is moving, and these actually abrade. Okay, so they are abrasive in nature, and the motion itself is, it's creating friction between the bedrock and the moving ice, and they scratch the surface of the bedrock. So you can see over here these marks, these linear marks. These are types of features, that are found on the at the bottom of the or on the surface of the bedrock on which the glacier has moved. So later on, when the maybe the downslope areas where the ice has melted off after the winter season, you can find these striations exposed on the bedrock, and from there you can understand that most of the erosion that might have happened or the sediments that have been produced in this region is due to this basal slip movement. Then the other one is called the plucking. So in plucking is that how we saw, there are the particles, the rock fragments are dragged down. So what happens over here is that there is more of a kind of a brittle kind of action that is taking place. So this is also an erosion process, and due to the this happens when your glacier is not warm based. So the contact between the glacial ice and the bedrock is not there is no lubrication between the two. The contact is, you can say, it is it's dry in nature. So what happens is there is no basal slip of any kind, there is no kind of slipping motion. What we see is the ice due to the obstruction that it is facing below the at the bottom of the glacier ice. So it kind of breaks off. Okay, so there is a little bit of tensile fracturing that happens. Okay, so the ice sheet might start breaking off, and because of this what happens, this you will find abrasion on the up ice side. Okay, on the opposite side of the direction of the movement of the glacier you will find, but at the bottom part or the downslope part of the mountain, you will find that the rock fragments are kind of plucked from the ground. Okay, so they are plucked from the bedrock and then they are carried forward, and the ice over here, it is not a single motion, it starts breaking off. Okay, because there is no the friction between the moving ice sheet and the bedrock is increased in this kind of glacier movement. So these tensile stress is arising because the ice is kind of being dragged along, but it cannot just have an easy slipping kind of a motion is not facilitated over here. So the pressurized glacial melt water kind of creates these joints, and they help in the dragging of the ice because of that. So these kind of features are formed. So you can see that the glacier must have moved in this direction. So while this part might have been abraded, these part you can see that there are kind of rock fragments that are situated over here. So this again is the example of plucking or glacial quarrying. These part is actually kind of plucked and carried ahead. These are also called rocher mountains. Okay, so this is an example of Roche Mountains. So now we saw that there can be two different types of glacier movements, and so what is carried along with them? Obviously the movements themselves will create certain kind of landforms, which we call erosional landforms. But the debris and the sediments and the rock fragments that are carried forward with the glaciers, they also get deposited in some places and they will again form a different kind of landform. So, what are these these sediments? In fluvial, we had seen you have suspended load, you have bed load. Okay, so similarly, even by glaciers, the kind of sediments that are transported by glaciers can be supraglacial. Okay, so I'm sorry, yeah. So these are actually transported on the glacial surface, and usually, they are usually formed by some adjacent uh, when the valley walls, okay, some valley walls, they are getting eroded, and any kind of rock form or rock block which is hanging on top of these glaciers can, they might undergo deformation, and then they fracture and they fall on top of the glacier. So these are mostly uh, they are bigger in dimension, and they are very irregular in dimension also, and they are carried by the glaciers, but they are on top of the glacial surface. Then you have the N glacial. So these are actually debris that are carried from the bed along the flow lines of the glacials. Okay, so you can see in this. Okay, so these are maybe uh, some part over here. Okay, there might have been some melting of the water or melting of the glacial ice that might have happened, and the weathered debris are trapped in that water, and they can actually flow into the glacial. Okay, so the water, as we saw before, maybe a tensile fracture has developed, and the melted glacial water actually carries these debris and flows into the those stress fractures, and they are then transported in between the sheets of the glacial ice. So this is a type of sediments and the sediment transport by the glaciers. Then you have subglacial. So these are the debris that are transported beneath the glacier. So mostly, as you can understand in a basic way, that these are the debris that have been plucked off from the bedrock, or or dragged along by the moving ice sheet, and they are carried by the at the right bottom of the right at the bottom of the flowing ice sheet. So you can see over here how the different kind of transporters have. Supraglacial is on top of the glacier, and glacial is within the ice sheets, and basal or subglacial transport is happening at the bottom. So mostly the erosional kind of work is done by the subglacial transported sediments, and most of the supraglacial transport and the subglacial transport are mostly those two form major kind of depositional landforms. We will see later on. So there are some different kind of flow patterns that happen in the ice. So as we were studying, how basal slip happens when you have warm base glaciers or wet bed glaciers. You can also have the frozen bed glaciers. So what happens with the frozen bed is that you mostly have only deformation of the glacier. Okay, so the tensile stress fractures that we had seen, so that is the kind of glacial the flow pattern that is seen in the ice. So the entire ice block may not move all together, but parts of the glacier, kinds of they fragment and they break off from the main ice body, the glacial body, and then they can deform and then move. Whereas the glaciers with wet bed, okay, so where you have the melted glacial water flowing below the glacial below at the bottom of the glacier, they also provide a different kind of movement, that is the slip movement, along with the deformation that happens due to the the it is owing to the principle of the the gravity and the weight of the ice. By the virtue of just the weight of the ice and the gravity that is acting on it, it will drag the ice towards the in the downslope direction, as well as the slip that happens between the glacial ice as well as the bedrock. So when glaciers have frozen beds, their flow is only from internal deformation that is within the ice sheet alone, and with the wet bed you have both internal deformation and sliding. Okay, so there are two this difference is seen in the the way the glacier flows. Even in this direction, in this diagram you can see how you have the basal slip in this direction, okay, which gives the plastic flow. But if there is no melt water, so the only kind of deformation that we can see is the brittle kind of deformation. So you mostly you will be able to see the deformation kind of flow in the top part of the glaciers, okay, because there is no melt water as such which is aiding in the slip or sliding kind of deformation. So top part you will find at many places you will have such fractures developing, and maybe the top part, as you know how avalanches happen, so it's usually not the entire ice sheet that moves, it's the top few meters of ice that break away because of this only internal deformation, and they can slide down. Okay, so that is the kind of movement that happens in the top few meters of the glaciers, because most of it is made up of unconsolidated snow, and if beyond a certain amount of accumulation, the area cannot hold that ice anymore. So the we have seen that glaciers are occurring in the polar regions as well as some high elevated areas. So on basis of that, you can have two kinds of glaciers. You have continental and alpine. Obviously continental are they cover vast areas of land, and mostly they cover uh, the entire span of the land in those places. So you have Greenland and Antarctica, whereas alpine glaciers, they originate at peaks, mountain peaks, and mostly in polar regions and some temperate areas. And alpine glaciers mostly grow due to the accumulation of snow over time. Okay, so you need precipitation, you need a good amount of precipitation for the snow to accumulate, whereas your continental glaciers are usually present in the polar regions, and these regions are always the places where you don't have mostly a lot of sunlight on a regular basis, and so the ice can below the freezing point, okay, over time. So based on these you can have obviously if there is only accumulation, so the entire time the glaciers would be only increasing in size, but that is not what happens, right? So you have, there is a balance of the accumulation of the snow and the say melting or displacement of the snow, okay, where the snow where the glacier actually moves down, and because of its melting we have plenty of river systems that originate due to the glacial melting. So we have that is why there is two kind of zones that are demarcated. So you have the zone of accumulation and zone of ablation. So zone of accumulation, as the name suggests, is where the snowfall is actually getting accumulated. So the rate of snowfall has to be much greater than the rate of melting of the glaciers, whereas in zone of ablation the rate of melting is more than the rate of accumulation. Some precipitation can accumulate in zone of ablation also, but that rate has to be below the rate of melting of the ice in that area. So there is an equilibrium line that is that denotes the that demarcates the the two zones, and this equilibrium line, if if it moves downwards and it moves towards the zone of ablation part, it slowly, that means your zone of accumulation is increasing, and less and less snow is getting melted. Also the amount of accumulation is increasing in size. So then again you can see it that in glacial period obviously this equilibrium line is going to differ than what we see in interglacial periods. So again this is just depiction of different type of glaciers. You can see that this is the continental glacier. There is a huge lateral extent of it. You can see it in Greenland and Antarctica, whereas this is the kind of an example of alpine glacier, where mostly the glaciers are formed in in big depressions between mountains, in valleys, and then they flow downwards down the slope, and then that is how their features are they differ from like most of the features. There would be some similarities, but for continental glaciers you will not see a lot of valleys being formed, because they are mostly covering the entire span of land, and the entire ups the downslope erosion is less, whereas in alpine you can see that this red dotted line is actually the equilibrium line, okay, and if this is the equilibrium line, then this is the accumulation zone, and this is obviously the ablation zone. So you can see that there is more thicker ice cover in the accumulation zone, and you can also see these cracks on occurring on top surface of the glaciers. So this is the top few meters can actually displace downwards when they increase in their weight and size. And you can see that there are mostly all the moraines that are formed, different kind of moraines are formed in the alpine glaciers, and in continental glaciers also you have moraines, but the frequency or the the number of moraines that occur in continental glaciers and the alpine glaciers will differ, because the movements are different. The already the existing topography of the area is also different. So there is another type of glacier that is called the Piedmont Glacier. So Piedmont Glacier is when the valley glacier, that is kind of the alpine glacier that is flowing downwards, they spills out in in front of the mountains and onto flat foreland areas. Okay, so you can see that actually this is a type of an alpine glacier itself, but it has come down, and instead of just melting and into the ablation zone, this area is maybe it stays under the freezing point and the ice doesn't really melt, and this again forms another large mass of accumulated snow or ice. So then it can be called as a Piedmont Glacier also. So again, this is just a diagram of, to make you understand what is the accumulation zone and what is the ablation zone. So mostly, this area will have, say, as we had discussed before, it might have internal deformation more, and towards the ablation zone, because increasing in temperature as well as, decreasing of the elevation, you can have, melt water, forming between the bedrock and the glaciers, and then you can have the slip motion and the slide motion. And as you can see at the bottom, you can find the melt water, kind of exiting the glacial region. So as we had seen in fluvial landforms and the rivers, okay, so you have similar kind of stages for the cycle of a glacier. So you have youth, maturity, and old. So youth is usually marked by, the erosional activity of the ice in a cirque. We will see what is a cirque. And mostly erosional landforms are generally created in the youth stage of the formation of the glacier, and the starting of the movement of the glacier from the place of its formation downslope. So it's mostly erosional work and erosional landform creation. Then in maturity, maybe there are two different glacial valleys that are present side by side, and both of them have started, the ice has started moving down. They can join at, downslope areas, and then they together can form a trunk glacier, and you can have hanging valleys starting. And also, more erosional work can be carried out by this glacial movement. And many the individual erosional landforms together, with subsequent erosion, can get transformed into another type of landform. Then in old age, mostly as we had seen even in rivers, like with age, the width of the valleys actually increase. So that occurs even when we are talking about glaciers. So you have U-shaped valleys, that is, that starts of the last stage of the glacial erosion. And you have plains that are forming, that are mostly covered by the sediments that are carried by the glaciers being getting deposited. And there will be more melt water related landforms that are created at the old age of the glaciers. And then most important glacial depositional landform that we see are the moraines that happen at the terminal stage of the glacial cycle. So first we'll go through the erosional landforms. So the topmost, or the place where the glacial ice is actually originating, they are called cirques. So they are usually depressions, bowl shaped mountain tops. And the sides of these cirques are mostly created by the plucking and abrasion. And then these slowly deepen, with more and more ice, glacial ice being formed, and also moving through the valleys. And between the you can have, if some of these cirques, they go beyond your melting point. And some of these glacial cirques, if they melt later on, they can form Kori Lake or Tans. So you can see over here, these are again kind of depression. And maybe the glacier has fully melted, and only some melt water is remaining. And they form a lake, so then they are called Tans. And if there are three consecutive cirques, okay, which are forming, and also they are eroding the the bedrock backwards, the valley backwards. So these three kind of cirques, they meet at one point that is called as a horn. You can see this is one glacier, maybe this is the other one, this is the other one, and the erosion has pushed the back wall of the valley, and then they start joining together, then they form horns. Arrates are these ridges that occur between two side by two adjacent glacier valleys. So these are all kind of erosional landforms. You can see horns. So this is like a pyramidal peak, and knife edged ridges between two cirques are called arrates. Then you have another erosional landform is the Paternoster Lake. So these are actually series of glacial lakes that are connected by streams. So over here, maybe once the a lot of all the glacial ice has melted, and numerous small lakes are formed, and but they are all connected together with a by a stream or a braided stream, as is mentioned over here. And these they form in a valley itself. They are not a part of different glacial lakes, but they are as small ponds that are left behind by the meltwater. Just wait a minute. So these are usually you can relate them to the youth stage. Okay, youth stage of the glacial cycle. Then in the mature stage, what happens is that you have some formations of U-shaped glacial troughs and ribbon lakes. So these you know glacial troughs. So all the imagine this entire topography when the glaciers are present. So the ice is moving down. Okay, so all these different places of accumulation, from the these different places of accumulation, the ice keeps moving down. So when they are moving down, they increase the valley width, and then they all fall into one big one large trough, you can say, or this U-shaped valley, and they again flow down. Okay, so this is the glaciers on the downward journey can actually are fed by these different glaciers that are present over here. And these these truncated spurs, if you see them, okay, so the spurs is like these are not cylindrical all the way. So they were joined at one certain point, and then they later on widen at the base of these these valleys, or these cirques that were created before. So these then together, when the glacial ice has moved down slope, and then all of them are joined together to form one big U-shaped valley. uh, so this entire trough is the U-shaped valley. And then these kind of over here you can see what happened here, like all these glaciers feeding into this glacial trough. Okay, so all these cirques are actually feeding into this glacial trough, and so this is the main U-shaped valley that has formed. But over here on this side, you can see a lot of cirques actually had fed into this valley, and this is called a hanging valley. So this is sort of a tributary to this main this main valley glacier that was present over here. So tributary valleys are also termed as hanging valleys. So you can have if these hanging valleys mostly later on, when we only see the melt water that is present, so these areas can actually get transformed into a waterfall also, depending on how much um, mm, how much discharge is actually coming from the meltwater. These are some more, erosional landforms that are present. So you can have coals. So that is when your two cirque basins on opposite sides of the mountain erode the aerate. Okay, we had seen that thin ridge-like feature between two cirques. If these, with with time, these cirques actually come closer, and then they join to form a cone. Okay, so the aerate has got eroded, and together the two cirques come together and form a cone. And you have another kind of erosional landform that is mostly associated with, you can think of it being associated more with the continental glaciers, where the valleys that are created by the glacial erosion, they actually meet the sea, or they are drowned by sea water, and they are called fords. Okay, so a lot of forts are present in Norway. So Norway is known for the forts that are created over there. So you can see over here. So this is actually meeting the sea, and the valley is drowned by the water, and the topmost layer of that the water body that is present over there is actually fresh water. Now we come to the depositional landforms. Okay, so we saw in the youth stage, and we also saw in the the mature stage. Now we slowly move on to the depositional landforms. So depositional landforms can form in the later part of the mature stage as and the old age, the old stage of the glacial cycle. So what are the most common kind of sediment deposits that we see, or what is the composition of these sediment deposits? So these are boulder clay or glacial till. Till is mostly associated with glacial sediments only, and these are usually unsorted deposits, and these are all the boulders and the different kind of clay minerals, and fine rock powder that is carried down by the glaciers. Erratics are actually big irregular boulders. They differ in sizes and the shapes, and then they are carried by the ice. You can say that these are mostly part of your supraglacial sediment transfer that happens by the glaciers. So these erratics, if they are found in one place, they can also signify, because they all are different, and they also have different origins. So it can give us an idea about the entire path that has been traveled by the glacier while it was moving. So glacial depositional landforms, as I said, moraines are the most important depositional landform that are formed by glaciers. So you have lateral moraines, so that is on the sides of the glaciers. You have medial moraines, so these are these usually are formed when you have two glaciers joining together, and the inside lateral moraines join together and form the medial moraine. Then you have the ground moraine. So these are the most of the rock fragments that were dragged beneath the glacier bottom, so the frozen ice, and then they are they form a moraine when the glacier has melted, and mostly these rocks, these ground moraine fragments are bigger in size, and then you can see them just getting deposited at the place where the glacier has melted. Then you have terminal moraines or end moraines. So this is eventually the the foot of the valley where the glacier has reached, and the glacier has not moved forward any further beyond these terminal moraines, and these are they kind of mark the end of the glacial valley that has been formed. And the recessional moraines are one kind of moraines that uh, these are by if the melting of the glacier, it happens in stages. So this is when your recessional moraines form. So they are a type of end moraines itself, but the kind of distance could be a bit different from the it can form, uh, it is not exactly the last terminal moraine or the last part of the glacier that is there. Maybe some ice has was left behind, and then with eventual later on melting, the it forms in the same direction as the end moraine. So these are your recessional moraines, and you can see over your outwash. So this is kind of the area where your uh, water, the melt water, the sediments that are carried by the melt water are deposited. So in a plain, they are just washed off from the glacial valley, and then they are they are just spread across the plain at the foot of the glacial valley. Some other types of depositional landforms are, these are actually most common in the continental glacier. Okay, so your moraines are mostly seen in the different kinds of moraines that we spoke about. You see in alpine glacial environments, and in continental glacial environments you can see drumlins. So these are these oval shaped kind of mounds of glacial sediment deposits, and these usually form beneath the glacier or the ice sheet, and the kind of the narrowing part actually points to the direction of the flow of the glacial ice. And if they occur together in a grouped fashion, they are also called swarms, drumlin swarms, and they look like a basket of eggs. Then you have eskers. So eskers are sinuous ridges. Okay, so mostly you will find them in irregular ridge type of topography, and these are actually all the gravels and rock fragments that align themselves in the direction of the ice flow, and then they got deposited in an irregular fashion. Then outwash plains are type of depositional landforms that you have seen even in alpine glaciers, and they are also formed in the continental glacial areas. Kettle lakes are are formed in depressions, and usually they are formed in between alternating between two ridges maybe. And cames are rounded hillocks, or when the sediments are accumulated in a dome shape, and small kind of hills are formed, and they are called cames. Over here you can see that end moraine is present even in the continental glacial topography. So end moraine, again, it marks the end of the glacial valley or the glacial extent beyond which the only melt water is present. There was no glacial ice per se. Now we move to coastal geomorphology. So we saw the kind of the uh, first you have the glacial geomorphology. Okay, so they are changing the landscape of the the earth at the start, or at the before the fluvial geomorphology that starts. And coastal geomorphology is again the in areas where you have the end of the river systems, and mostly the obviously the river meets the sea, and that entire part is actually there is mostly the interplay of fluvial as well as your coastal processes, the wave action that we see. But there are some geomorphic landscapes and landforms that are mostly only formed due to the wave action. Okay, so not only do fluvial geomorphology for plays a role in the different landforms that are created at the coast. But most importantly, there are a lot of processes as and formation of landforms that happen due to the wave action of the the sea water or the ocean water that is present along the coast. So, in coastal geomorphology, we will focus only on the landforms that are created by the waves and currents and the sea level changes that we see with prolonged action of sea water in that sense. So, as I said, coastal geomorphology is the study of morphological development and evolution of the coast under the action of winds, waves, currents and sea level changes. So, the waves themselves, they have different sort of wavelengths and movements from the deep sea area to the shoreline area. So, the source of energy for the coastal erosion and sediment transport and deposition is mostly by the wave action. So, when the wave is moving from the deep water to the shoreline, the movement itself actually creates the potential energy and then it converts that energy into the kinetic energy, which eventually serves as the cause or as the origin of the the transport of both water as well as the sediments. So, this kinetic energy is actually is the reason behind which reason behind the different kind of erosional and transport as well as depositional changes that we see along the coast. So, the wave energy that is present, that is actually giving rise to these changes along the coast is due to the frictional effect of the wind that is moving over the ocean surface. We know there is a wind actually that is moving over the water surface, drags the surface of the water, and because of this dragging of the water, there are kind of circular motion of the water molecules at depths that creates the that drives the movement of the water further. So, it is not a linear kind of movement that we see. It is first in a circular fashion that happens at the depths, as you can see over here. Okay. So, but the circular motion is more evident at the at depths closer to the surface of the water, and then you can see that how the circular motion actually drives the water towards the shore, and towards the at the shore you mostly have linear or kind of a vibratory motion of the water, and this motion then actually crashes the surf areas where the water crashes with all its momentum that has been created from the deep water area all the way up to the shore. So, the moving waves do not move the water itself forward, but the waves impart a circular motion to the individual molecules of water, and this circular motion is actually pushing the water towards the surface, towards the shore, and at the shore it is more or less a linear motion, and then there is a sudden drop in the or sudden stop of the motion, and there is a the again the wave action itself actually drags some of the material that is present on the shore back towards the sea. So, this is a cyclic kind of a process that we see. So, the sediment and the water is actually moving towards the shore, and then some part of that sediment is dragged back into the sea. So you have different kind of water processes. So you can have the for the shallow water processes, these usually happen closer to the shore. And then you have wave refraction because of say because of the present topography, or any kind of a rock fragment or a rock feature that is present over there. You can have a wave refraction, or due to changes in the wind direction and the speed of the wave, then you have wave diffraction. So this is where actually your rock fragments or rock features actually cause a deflection in the direction of the wave crest, and it can change the direction of the sediment transfer also. So those were related to the waves. Now you can also have currents. So currents are usually they are the actually the direction of the transport of the water as well as sediments, okay, with respect to the waves that are present over there. So over here you can see that there is the movement of the sand can happen along the shore, but in a different kind of a pattern. So over here you can see that there is a half cyclic a wave pattern. So this is due to the longshore drift of the the longshore current that is present over there. And mostly uh, the landforms, or the deposition that happens, those are usually generated by the different currents alone. So longshore current will have longshore drift of the sediments that are being carried, and then you can have littoral drift also. So these are all along the shore that is there. Then the beach drift is mostly the recurring, the frequent incoming water and the water going back into the sea. So this action also itself causes a different kind of land sediment transport and deposition also with time. So you can see over here the littoral drift is actually the movement of sand grains in the direction of the longshore current. So this is your longshore current. So along with the the wave action that is happening, there is a parallel. There is the movement parallel to the shore also. So that is your longshore current. So and this moves sand from one coastal location to the next. Okay, so this actually enables the elongation of the beach area. Okay, so the if the beach area is increasing in length, mostly this is due to the sand transport from one area of the beach in a lateral fashion to the other location. For the beach drift, this is actually causing the the extent of the beach area towards the sea. Okay, so this is this maintains the you can say the shore line of the of the coastal area. So that is done by the beach drift, or the the beach current, that is the swash and back swash currents. Another important driving factor of formation of coastal geomorphic landforms are the tidal processes that happen. As we know that due to the gravitational pull of by the moon as well as sun in some cases, you have different kind of tides that occur in a periodic manner across the day on the earth's surface. So it's a periodic change of the water level. So you can have a high tide or a low tide, and mostly when we talk about diurnal tides, so you have two high tides and one low tide. Then you can have semi-diurnal tides, so you can have two high tides and two low tides, but the high tides are not the two consecutive type of tides, maybe two high tides and the two low tides are not equal in their in their magnitude. So the, as you can see, the crest of the high tide is different from from one to the other high tide, and similarly in the low tide you can see that. Okay, mixed tide is where you can have higher high tide, lower low tide, and also there is no certain the wavelength differs, as well as the tidal period differs in one tidal day itself. Okay, so these are different kind of tides that are observed, and mostly the tidal currents actually they transport the sediments, they erode the sediments, and they themselves again aid in formation of landforms or changing of the geomorphic the coastal geomorphic scenario. And then you have microtidal, mesotidal, macrotidal ranges. So these are the kind of differences that we see in the tidal waves that are created. So the factors which govern the kind of tidal processes that we see is the tilt of the earth's axis. So as we had seen before, the different kind of the heights, the different heights of the high tides and the low tides are actually due to the tilt of the earth's axis. So it is not uniform. If one point, if we consider only one point of the earth, okay, so if this is your earth and we know the it is tilted, the axis is tilted, and if suppose the high tide is happening in this sense, okay, obviously it does not look equal over here, but just imagine. So this point over here as whole, this is the uh, the wavelength, or the amplitude of the high tide over here at this certain point of time. But when this point actually reaches over here, you can see that the amplitude has increased. So this difference in the amplitude of the high tides is due to the tilt of the earth's axis. Then the moon's orbit itself. So in the aphelion, when the earth reaches the aphelion part or point of the moon's orbit, and the perihelion point of the moon's orbit, so the again the amplitudes of the high tides and the low tides are going to differ. So you will have um, exaggerated high tide when it is closer to the when it is at the perihelion, that is closer to the moon in of the moon's orbit. And then obviously sun's gravity plays another role in the type of tides or the tidal currents that are present. So over here if I change, yeah, shift this, so you can see in the spring tide, when we have spring tides, all three are in array are positioned in a linear way. So you have all three of them, the earth, moon and the sun are positioned linearly. But in neap tide, the moon and the sun are at 90 degrees from each other. Okay, so they the earth is actually the point, and you have the angle between the position of the moon and the sun with respect to the earth is actually 90 degrees. So over here you can see that you have neap tides, and again you see different kind of the amplitudes of the tides are different. Over here you can see the amplitudes of the tides increase when you have spring tides, because the pull of the due to the moon and as well as the sun is going to have an effect. So now we come to the different zones that are present in the coast, and because of this you will have different kind of coastal geomorphic processes happening. So you have the coastal zone, that is the transition zone where the land is actually meeting the water, and mostly the wave action is prominent in this area. Then you have the coast. So this is actually the strip of land where indefinite width that extends from the coastline inland. Okay, so this is where your topography might change. So mostly it is they feature cliffs, frontal dunes, and you have vegetation. So you can say that it is the entire part from the uh, the coastal the shore, okay, all the way towards the inland, where you can think that the coastal geomorphic processes are not playing an active role. Okay, so maybe if you can see dunes, coastal dunes are present. So the area behind the coastal dune can be can be considered inland, and as the last point of the coast that is present. Then obviously the shore, so that extends from the low water line to the normal landward limit of storm wave action. Then you have shore face, so this is actually the towards the when we are going towards the sea. So this is the seaward dipping zone. So from the lower water line offshore to the beginning of the continental shelf. So the entire the slope, the continental slope part is the we can go till sorry, continental shelf is this part over here. Okay, so this is the shoreline. Okay, so the this in this part where you still have the near shore area. Okay, so the near shore area. So this part is kind of your shore face, and beyond this your continental shelf area is actually starting, and this is also the shallow sea floor. Okay, so this is where you have the kind of the boundary of where your continental the continents at the continental area actually ends. So that is the the continental shelf, beyond which you have mostly your deep ocean or the abyss that we say. And this is where your continental slope begins. So the direct gradient where your uh, the gradient that we see from the continent all the way to the ocean floor. Okay, so this is where that is the end of the continental shelf. Okay, so beyond this part is about the continental shelf, and then it ends near the starting of the abyss or the ocean bottom. Then we have the beach profile. So the beach profile has seasonal changes. Okay, so you can have a summer beach. So during summer your beach actually is how we had aggradation and degradation. So during summertime you have aggradation, that is accumulation of the beach sand, whereas in winter time most of the a lot of the accumulated beach sand is actually is eroded away by storms and stronger wave action. So so during winter the wind speed is much greater, and because of this you have the erosion mostly, and also the water. Okay, so the extent of the water inflow into the coastal parts is more in the winter time. Okay, and you can see over here that mostly the dunes are formed during summers, and also another feature called berm. We will see in the later slides what they are. So this is actually the beach profile. So you actually calculate how the beach profile looks. We calculate the elevation at every point in the direction perpendicular to the the beach front that we see, and we can try to understand whether with if you plot beach profiles at different times of the year, you can see at what time the beach was actually increasing in say whether topography is mostly aggradation in nature, or when the topography in that beach is actually degrading in nature. So this is a quick, kind of classification of, the erosional landforms that we see and the depositional landforms that we see due to coastal geomorphology. So mostly your cliffs, notches, anything that is actually eroding the land, as well as eroding the sand from the beaches. The features are formed due to this action of the waves, and any places where the waves are actually depositing that transported sand or fragments or sediments, that is where you have the depositional features forming, like beaches themselves are depositional landforms of as part of coastal geomorphic processes. You have spits, tombolos and bars. So the most kind of gradual uh, formation or the gradual change in the coastal geomorphology due to erosion action of the waves can be seen in the development of cliffs. Okay, so these are usually the steep rock faces that we see, almost they are vertical in nature, and these are formed right next to the sea. And because the sea actually keeps eroding the base of the rock, so over here consider this as your the cliff was like this in the start. Okay, so with time this starts getting eroded. Okay, over here also you can see that if the wave erosion is happening at this point as well as this point and this point, so you can see a cave is kind of created over here. With time what happens is this entire part actually collapses. This headland starts collapsing when this area becomes this pillar actually is eroded away, and it cannot support the top part of the cliff over here, and this actually falls down. Then this becomes your new cliff. Then slowly again this will get eroded over here, and it cannot support the top, and then this will fall down. So this is how gradually the sea actually kind of incises into the land by wave action, and more and more cliffs are formed, and all these dropped kind of big rock masses are later they are actually called sea stacks. So we will see that. So with the continuous erosion that happens, wave cut notches are formed, and at the base of the cliffs, and these are when they increase in size, and with time they will form new cliffs. And wave cut platforms are also seen, where the over here you can see with time this notch is actually going to start incising inside. Okay, and slowly this area gets abraded and smoothened, and you can have wave cut platform that is created. Maybe this entire this also gets eventually and gradually this also gets eroded in a way that it is actually either supporting it, or there is a gradual kind of decrease or the reduction, or you can say receding cliff wall that keeps going towards the inland area. So this is actually the cliff face. So the cliff face, you can see over here that the cliff face was over here initially, and now it has retreated back over here. So this is your new cliff face that has formed, and this is the wave cut platform that slowly becomes smoother in the appearance at the base of the platform. Then sometimes we have heard these two terms, headlands and bays. Okay, so usually headlands are those are more resistant to erosion than the bay areas. So this area is actually more prone to erosion, and slowly what happens is you can see that since this is made up of softer material, it has gotten eroded faster than the headland. Okay, and slowly the water is going to inject this entire area and erode this area, and we will have a bay between two headlands over here. So this actually we can also see in the case of Bay of Bengal. You have the Indian coast, the east coast in this part, okay, and then you have Myanmar over here. So these two areas obviously are not that are eroded to that extent as this area. So mostly because this area is actually also the area where you have the delta, and it's easier to erode and incise uh, this area between the two headlands. Okay, so this is a kind of an example which explains how bays are created. So headland is a rocky coastline, and bay is usually found in the coastline between the two headlands. So again, caves, as I had explained before, when with the subsequent erosion at the base of the cliffs, obviously there is erosion happening at the cliff face also. But if this is an headland area, so obviously it's going to have opening for erosion at the sides of the cliffs also. So sometimes the erosion can also happen on the sides of the cliffs, not just at the face, like at the front of the cliff. So these areas can actually form the caves. Okay, so with repeated erosion over here, in this region also you can have clay formation of caves in that place. And with time again, if the two sides of the cliffs, the caves have now got intersected, and it has kind of eroded through the cliff, or eroded through the headland area, so it can form kind of an arch over here. And slowly with time, this top part cannot be supported by these two kind of pillars that are present, rock pillars, and this will actually break and fall down, and this will be the new cliff face that is formed. And this is kind of a remnant of a past cliff, and this is called a stack. And sometimes as you can see, the stack is undercut and collapses, and this leaves a stump. Okay, so maybe initially when this cliff face was forming, the there was a rock mass present over here, but it could not be supported by the bottom part of the cliff, and it might have fallen down, and now it has formed a stump. And this is called a stack that is remaining, that is between the an arch might have formed like in this portion, and the roof of that arch actually had fallen down. Okay, or it obviously it got eroded away, and then this section is actually separated from the present cliff face that we see. So this is all due to abrasion and hydraulic action, and these actually start widening the fractures that are created by the consistent waves that are hitting and eroding the rocks over here. Now we come to the depositional landforms. So the first very important depositional landform that we see are called spits. Okay, so these are all mostly formed due to the longshore current. We had seen, it's mostly trying to transport the sediments in parallel to the shore, parallel to the shore. And because of that, or any deposition that is happening, actually they occur parallel to the shore itself. And spits are such narrow ridges of sand that that are formed slightly away from the coast into the sea, but they are sometimes kind of attached to the main coastline also. And the formation of the spit as is due to the change in the direction of the coastline, or where the wave action has actually decreased in energy, and maybe that is uh, the current direction might have changed at a place where the you have inflow or the outflow of the river water into the sea. So that flow can actually cause some deviation in the current that is flowing over there, and change the kind of energy of the waves that are present over there. Then similarly you can have bars. So these are formed in the same way as spits because of longshore drift. And again these are formed in areas where the wave energy has gone low, and mostly they are the rate of erosion or rate of transport of sediments is much lesser uh, than the depositional part, because obviously you have low energy wave action in these areas. And so these are different types of depositional kind of features that we see. You can see barrier island, that is actually when the bars or the there might have been separate bars before, but slowly they actually merge together to form a longer strip of land, that is a barrier island. You can see over here you have a bay, okay, and you have a bar at the mouth of the at the mouth of the bay. Then you have a spit over here. The current has actually changed. So spit is usually formed at places where you have wave diffraction. Okay, so the change of the direction of the current can happen, and due to which your sand spit are formed. So it is like a small curved kind of a bar. Then dunes are again a very important depositional landform that are created by coastal geomorphic processes. As we had talked about, the summer beach profile and the winter beach profile. So most of the dunes that are associated with coastal landforms, geomorphic landforms, are formed in the summer, during the summer beach profile. And sometimes due to increase, maybe storm activity that has happened, some part of this dune actually gets eroded, and and there is a sudden slope gradient increase in the slope gradient that has formed near to the area where the beach meets the water. So this area is actually called a berm. Okay, so these can happen during due to the swash and the back swash action that we see on the beach, and the increase in the the water level that we see during the summer time. Okay, so there is no uh, mm, the action is not that strong to erode the entire deposited dune or beach sand that is present over there, but it it can cause a sudden change in the slope in that at the beach front, where the water is meeting the beach, and the storm action is a bit stronger compared to the dunes that are created in the towards the back of the beach area. So you can see that the backwash that happens has little less energy to carry all the sediments down to the beach into the sea, and the beach is still growing, but there is a sudden there is a slope that is formed over there. Okay, so these are called a this is called a berm, and this is the berm crest. And as you can see, there is a dune away from the sea. Marine terraces can give us an idea about the sea level changes that are present. Okay, so you can see over here that maybe this is the present, you know, uh, maybe this is not the present as such, but there are three different terraces that are present over here. and at time 1 this was your main sea level, okay, and at time 2 you can have this was the main sea level, okay. So this is if your tectonic uplift is happening, your marine terraces are preserved, okay. So marine terraces are similar to the wave cut platforms that we had seen, and these are usually uh, you know formed where at the main sea level area only, okay. So where the main sea level is actually mostly doing all the erosion work and creating the wave cut platforms. Now with respect to the main sea level, the marine terraces are either exposed or they are not exposed, and as well as the changes in the tectonic tectonic uplift or subsidence in that area also can govern whether the marine terraces are exposed or not, okay. So you can see that this is a preserved marine terrace, and this is the conceptual model that has that was put forth to explain this preserved marine terraces that we see, okay. So actually if there was no tectonic uplift, so this would have stayed below the MSL, okay, and it might have undergone that wave action on a repeated basis, and it might have got destroyed, okay. But since it was brought above the main sea level, it was no more eroded, and that is why it is preserved, and that actually gives us an idea whether there is a sea level rise that had sea level fall that had happened, or there was a tectonic uplift that had happened, okay. So wave cut platforms can be removed from the interaction of high energy wave regime by either global sea level changes or tectonically rising land masses. So this is what we can marine terraces are important to understand the different sea level change scenarios that we can see. And similarly the shorelines that are present right now, okay, at the present day, is not necessarily where they were present few years back. Either paleo shorelines are mostly seen when the water is no more the shorelines is no more submerged below the water, okay. You can actually if you take satellite images, in some places you can actually point out where the shoreline must have been a few years back. So mostly you can see a linear trend or some linear feature that can point it out. So suppose over here this is the modern shoreline angle, okay, and this is the you can consider this as the modern shoreline, and this is your sea cliff. But over here you can find that there was a linear feature present over here, and there was a sea cliff over here. So with this you can see that the shoreline has actually extended towards the sea, and this means that actually the sea level has actually gradually reduced in this area. So you can see the shoreline that was present a few years back, and if you can see the shoreline which now forms the part of the inland area, okay, so now you can see it. So that means the shoreline has actually transgressed, okay, in towards the sea, and the sea level had fallen, and which is why we can see the present shoreline towards the sea compared to your paleo shoreline that is present. So you can see that you can have, if you have low stable sea level, okay, so the deposition that happens, okay, so more and more sediments will be carried towards the sea. So the shoreline actually extends towards the sea, but with if there is high if the sea level is increasing, so the deposits Okay, so the beach deposits are found below marine deposits. So marine deposits is because the water is, you know, present on top over here. Okay, and the beach deposits have shifted backwards. And so because the sea level has risen, the previous beach deposits or transgressive deposits, as they are called, are actually you know, can be found underlying the marine deposits that are now present. So again, the study of paleo shorelines can actually help us in understanding the different sea level changes that has undergone you know, in the past. Now, there are few water bodies that are formed as a part of coastal geomorphology. Okay, so you can have a lagoon or an estuary. So, lagoon is actually a you know, shallow body of water. Just wait. Okay, so lagoon is a shallow body of water which actually occurs along the coast itself, but it is separated from the ocean uh, and but separated from the ocean, and there is a small kind of you know, inlet that actually connects it from the ocean. And mostly it's a combination of both you know, the saline water that is you know, you know, part of the ocean, as well as it is all there are inputs from the fresh water bodies also. So lagoon itself has, you know, brackish water, as we say. So you can it can have one or more inlets from the ocean part, but it is actually separated from the ocean. So you can see over here that this is the small inlet that is you know, actually transporting some of the ocean water or the sea water into the lagoon over here, and it is separated by a, you know, a bar or a spit that we had seen before. Whereas estuary is where your fresh water is actually meeting the ocean. Okay, so you can have lagoon, as we know, mostly it should be you know, uh, ocean water or saline water, but there are some lagoons which are also fresh water. Why? Because the input of the fresh water is actually greater than the input of the ocean water. So for example, you have Chilika, so it is actually a kind of a, you know, uh, freshwater lagoon, and it is really large, and it has a different sort of ecosystem, you know, which is supported by this you know, unique combination or unique proportion of you know, seawater to freshwater that is present over there. So lagoon does not necessarily have to be you know, an area which is connected to the rivers. Okay, it does not necessarily have to be connected, but an estuary is present only when there is a fresh water you know, meeting the ocean, and it is slightly separated by the ocean water by as you know, a sand bar deposit. So as we can see that the main difference between lagoons and estuaries are the flow dynamics. In estuaries, the river flow is fast and strong, while in lagoons, the water is shallower and there is not much, you know, transfer or the, you know, ingoing input and the output of the water happening. So mostly it is stagnant in nature, and estuaries are deeper than lagoons. So barrier islands, I had you know, said before that waves are repeatedly depositing sediment parallel to the shoreline. Okay, so and you know, barrier island again, you know, can help in um, separating the lagoon from the ocean body, and you can see this is a mainland and there is a spit, okay, that is forming over here, and it is separating the lagoon from the ocean, and the longshore current is actually increasing the width of the barrier island over here. Now another important, obviously an occurrence of tsunami is in, you know, is a consequence of underwater earthquakes, but tsunamis also you know, have a large role to play in the you know, changes in the coastal geomorphology that we see. Okay, so this is kind of basic diagram to understand the how tsunamis are formed. So mostly it is due to the tectonic disturbance that happens at the ocean floor, and due to which the water above that area is actually displaced, and because of this displacement, the circular motion that we had studied, for the wave processes that are occurring, they actually start building up the waves, where the wavelength and the amplitude of the waves start to change than the normal levels that are there. And when they approach the shore, the size of these or the amplitude of these waves actually increase, and the wavelength kind of decreases. And then at last you have the impact where the high amplitude waves are actually crashing on the shore. So this is the general understanding of how the tsunamis waves are forming. So the most commonly known disastrous tsunami that we have actually seen, or that we have experienced in the last few years, is the Sumatra and the Man tsunami. So as you can see over here, so there are two kind of movements that happened at the at the junction of the continental plates, as well as in there was the thrust faulting happening within a plate itself. So it was like a decoupled effect of two different kind of fault movements. So you have a thrust fault movement as well as a strike slip fault movement. This happened between two different plates, and this happened within one plate itself. Okay, and because of these two, there was a very the tectonic disturbance was too high in magnitude, and because of that, the build up as well as the amplitude of the tsunami waves created by this earthquake was very large, and it actually traveled great distances very fast, and it obviously had very disastrous effects. So this is kind of animation of how the tsunami waves actually got generated because of the rupture that had happened. So this video is about the how the rupture actually took place, and this was the effect of the the tectonic disturbance that had happened, the wave propagation that happened, and because of which the creation of the tsunami waves. So these actually waves traveled much further okay, in distance, and actually created the damage. You can see that a lot of wave interference patterns kept happening, and they kind of traveled across that entire area. So as you can see that because of the crashing of the tsunami waves, a lot of erosion happens at first. There are places where the large sand deposits are actually destroyed. So over here you can see that these were actually the kind of sandbars that were there, and this was before the tsunami had occurred, and after the tsunami you can see that most of these bar deposits were actually washed away, they were damaged. And you can see over here this area, okay, was actually destroyed. But with time, and because of the long shore drift of the sands, the sandbars are now again starting to connect over here. So you can see that while obviously the depositional landforms get destroyed with the occurrence of tsunamis, but once it has settled down, these the geomorphic processes, the coastal processes actually get back into their normalcy, and then they start building up these processes again. Another way to study past tsunami occurrences is the changes we see in the growth patterns of the corals. So over here, corals actually do get damaged with obviously by changes of the in the sea level, in the main sea level, and it can have the occurring partial damage, or entirely damaging the corals that are present. And in the case of the 2004 tsunami, a lot of local reef areas actually got destroyed. And over here we can see how the corals can help us in understanding the sea level changes that actually happen, okay, while before the tsunamis and after the tsunamis. So it can help us in understanding the frequency of the tsunamis occurring in that region. Okay, so yeah, so actually corals grow up to the sea level where the low tide is occurring. So if this low tide level changes, then the growth pattern of the corals change. As you can see that the coral has grown and it has now reached the low tide level. So beyond, the coral will not grow out of this water, okay, above the water level it will not grow. So what happens is it starts growing from at the sides, okay, it starts growing on the sides. So as you can see that if it starts growing on the side, so the layers will be created in this pattern, okay, so the subsequent layers will be also created in this pattern. But if there is a sea level rise, as you know, after tsunami usually there is a huge there is a substantial sea level rise. So now the low level the low tide level has increased, okay. So now what happens is this sideways growth continues, but this the the vertical growth, the vertical upwards growth is also continuing. So you can see later on that this starts growing in the upwards manner. But if the because of the tectonic if there has been a tectonic uplift in this area, okay, due to which the tsunami has already occurred, and the coral has actually brought above the surface. So what happens is the part of the coral that is actually on top of the sea level, this actually dies, okay, and this gets damaged, and the coral that the part of the coral that is below the water surface keeps growing in the in lateral fashion then, okay. So this is how past tsunami can be studied using corals. And again, this is a change in the geomorphic landscape that we observe in the coastal region. So tsunamis play an important role in the changes that we see. So these changes are very sudden, okay, so these do not take a very long time to be observed, because the sea level changes and the uplift, the tectonic uplift, they happen suddenly. And hence studying these changes in the say arrangements of the sandbars or these coral or the growth of the corals, so we can try to understand the uh, how many times the past tsunami occurrences have happened, if these growth patterns actually studied on the corals. So that's all. So we are done with the coastal geomorphology. Also we have done glacial geomorphology, we finished fluvial geomorphology and tectonic geomorphology. So in the last week of the geomorphic processes, we will learn about the aeolian. So that is due to geomorphic action of the winds. So that we will do in the next class. So thank you for attending. If you have any questions or doubts, please to put it in the discussion forum, and I will try to answer them over there. So thank you for attending, and hopefully I will see you in the next class.